we derived everything we possibly could for a 3D particle in a box, but we have yet to look at an expectation value for something in 3 dimensions. So we're going to use the particle in a 3D box to investigate this because we're going to utilize this mathematics and these ideas later on when we start talking about actual atoms and whatnot. After we do that, we're going to talk about how do some of the wave functions look, and we're going to visualize those wave functions. So I sent a panicked email to you guys right before class that has to deal with the visualization of this stuff. So first, let's talk about the expectation values. Okay. If we have some generic wave function, that depends on x, y, and z. And we wanted to know the expectation value of a. What's the integral going to look like to get the expectation value of a? Yep, so we need complex conjugate of this wave function. What do we need wedged in between? Yeah, a hat, some operator. And then what do we need on the other side? Yep, just our regular old wave function. Okay, what things am I missing? We needed. Right, you could leave it like this and have a d tau. We've specified the independent variables, so let's do it with a dx, dy, dz. Okay, so what does that mean we need for integrals? How many do we need? 3. Yep, triple integral time. Woo! Okay. If you assume is separable, this integral could change. How could we break this apart? Yep. So let's say you could break this guy apart into x. So you have the wave function, or the portion of the wave function that's only dependent on x. We'll put a little sub x underneath here to indicate we've changed it a bit. What's going to be wedged in between? Yep, a hat. In some cases, you may even have to break a hat into contributions, individual directions. And then what are we going to have on the other side? Yep. Yep. We don't want to add. We want to multiply. Yep. And then we would multiply the same thing for y in this case, right? Y. Sorry, I'm eating while we're doing this. I have a fireball. Does anybody know what fireballs are? Yeah, they're delicious. I love them. I found out they are like done making them. So my mom has like a stockpile of fireballs. The last fireballs in like Western New York are in her house. she's a doom prepper like I am, so she has a bunch of like food. So when I don't want to go shopping, I just stop at her house. And then we need Z. All right. And then what do you know about each of these integrals along here? Or what do we have to specify in here? Yeah, x sub 1 to x sub 2. They each have different upper and lower limits that we would have to integrate across. Does this look like easy math? Yeah, it's all slapped together, it looks worse. This does look bad, but we're going to use some mathematical properties that we know. One big one, orthogonality. What does orthogonality mean? 0 and 1, if they're the same wave function, it's 1. If they're different wave functions, it's 0. Can we do that, though, if there is an operator in between? No, we have to do the operation first, then see what happens. So in this case, yeah, this one would suck. But we're going to see situations where you might not even have this component. It might be 1. So you might have an operator that only acts in the y direction, and these other two have no impact. So you could just assume, well, we'll see. Let's look at an example of one where we consider that. So we're going to look at a particle in a 3D box with some set wave function, and then we're going to consider what is the momentum in the y direction. Am I okay to erase this stuff? Okay. Integral time. As an example, find the expectation value, I guess I should have given more space, of the momentum in the y direction for the 3D wave function x, y, and z, BC sine of nx over a, n sub y over b, and z pi z over c, where n sub x is equal to 1, n sub y is equal to 2, n sub z is equal to 3, 1, 2, 3. I know this is a really direct question, but what are we looking for? Yep. What information do we need to know? Yeah. Yeah. All of that stuff. Okay, what do you suggest we do first then? We can do that. What I would suggest is to write the full generic thing first, then break it apart. Just because sometimes, like this operator, it's very clear what, like, do you remember what py hat would be? Yep. Right. So what is the only coordinate that's really going to be affected by this operator? Y. So in some cases, you may not know that that's the case. This one, it's really clear cut on what it is because it's just in Y. So usually it's a good idea to start with generic, then work to more specific. So, but that your thought pattern is exactly what we're going to do. So let's write the full integral of what we're looking at. Okay. We got, what way do you guys like to do it? Do you like to do X, Y, and Z? Or do you like X, Y, Z? No? Okay, I always do X, Y, Z. Does it really matter? No, it doesn't, but that's what I like. Okay, so integration limits for the first one for X. We're going from what to what? And what is it for this wave function? Since we're talking about a 3D particle in a box. Or what's our upper? A. Yep, 0 to A. So what would it be for the Y? Yep, 0 to B. And then for Z? Yep. Just because for a 3D particle in a box, that's what we have set everything to. Is that wind current too bad? Or, all right. What next? Yep, we need the complex conjugate of this guy with these numbers plugged in. Is it going to change anything taking the complex conjugate of this guy? Why not? Yep, no y's. If there's no y's, you don't have to worry. So we can just write this thing in. What does the first term become? Pi x over A. Second term. Yep, 2 pi x. Oh, 2 pi y over B. Last one. Yep. Okay, we already said what the operator is, so we got to wedge that operator in. And then that's going to be operating on that wave function again. Oops. Pi x over A. If I say these terms out while you're trying to write stuff down, does it confuse anybody else? No? Okay, me, I'm really bad that way. I can't do it. That's like when people rattle off a chain of numbers. I gotta write it down. I can't do it. All right, what else do I need in here? Yep. I know. That's not the longest one we're gonna do either. Yeah, great. Okay, Lily, you said let's break this thing up into its individual components. What things could we do to make this simple or simpler? Anything we can pull out? Yep, we can multiply these two things together because they're just constants and pull that out front, right? So we're gonna get 8 ABC. Times, let's break up the X stuff. We'll use blue for that one. So we got that term, or that symbol. What other things go in with the X? Yep, we're going to square it because looking at this operator, does that operator impact that term at all? No. It's a partial with respect to y. This is just treated as a constant, right? And we got that thing. What I'm going to do, actually, what would the normalization constant be for a 1D particle in a box? 2 over a. So if we look at just the x component, it would be 2 over a. Sine pi x over a squared dx times, let's get the y stuff. We're going to have 2 over what is our normalization constant here? Yep. Okay, what has to go in there? Mm-hmm. Yep, this thing, that guy, and the dy, right? One. And then we got the normalization constant. Well, I got purple. We use purple. Oops, should have underlined that one. What's going out front for the normalization constant for z? Zero to c. What terms are going in there? Yep. Yep. Three pi z over b. Oh, why did I put b? That's terrible. Okay. This still doesn't look great, but you know some stuff. All of that stuff lumped together, what's it going to give you? This will give you a over 2, that integral will. So you'll have, this is 1. Because it's been normalized and it's orthogonal. What about that portion of stuff after it's all together? 1. So really, what we have to do is just this integral. Oops, let me give myself enough space. 2 over b, or at least this math, excuse me. Partial y okay. This went from something that's way more complicated to something that is way less complicated. And again, we use the idea of normalization and orthogonality to reduce the x term and the z term to 1. So now we just have to do that bit. So let's go through and do it. Am I okay to erase like this half of the board? Okay, so now we've distilled the expectation value down to this. I'm just rewriting it so it's easier to see. Okay, now it's just mathematics at this point. What do we need to do first? Or what would you suggest to do first? Yep, we could do that partial derivative. The other thing I would do, we're going to pull these constants just out front. We get negative 2i h bar over b, integral from 0 to b, 2 pi y b. Which way do operators always act? To the right. So we can leave this guy alone. We got to take the derivative of this thing. What are we going to get out? Yep. What now? So we're going to get what in total? Oh, I'm missing a pi. Sorry. Yep. Okay, what now? Yep, I'd use the table of integrals. So from table of integrals, we're going to go with this guy. In our case, what's our b equal to? Yeah. Annoying because that actually has b in it. Yep. We'll call this guy b prime. And that'll make the demons in my head shut up. Okay. So negative 4 pi I h bar b squared. What are we going to get out of this integral? B, yes. Whoa, got stuck. Didn't put a B. No, I didn't put a b prime. This is really hard to see. Okay, what else? Yep. And what do we got to evaluate that? Okay. Let's look at our limits. Sine squared 2 pi y over b. If I go to b, what does this portion in here become? 2 pi. What do you know about sine of 2 pi? Yep. What about if I have a 0 in here for y? What's sine of 0? Still 0. What's this integral going to work out to be? 0. No fun. Okay. What does that physically mean, though? What is the average momentum of the particle inside the 3D box in regards to the y direction? 0. So half the time it's moving forward, half the time it's moving back. There's no net momentum. So does the particle still have momentum, though? Yeah, particle still has momentum. It's just on average, it looks like it doesn't. So while the particle has momentum at any given time, its average or expectation value is 0. Okay. So we're going to utilize the separation of variables several times as we go through this course, and especially as we get to bigger systems and more chemically relevant systems. Okay. So that's how we deal with expectation values. Let's try to look next at some of these wave functions and see if we can decipher them from what are known as contour plots. Before we move away, does anybody have any questions about how to do this sort of thing? Yeah, we could have pulled that out way at the beginning because it's just a constant. So like at this part where I erased half of it, we could have just pulled it out there. Yep. Any other questions? Okay. Try to go through a couple of examples like this, show that you can pull these things out from one another, and just try to reduce it down to something more simplistic, even if you don't do the integration itself, but just the process of doing that. Okay, I'm cool to erase this.